Welcome to Module 3. In this module, we're going to treat other topics to finish the course. And this is the first submodule of Module 3, Submodule 3.1. The first set of topics that we're going to look at in this submodule is the transient circuits, first order circuits. We're going to look at RC circuits, we're going to look at LR circuits, and then we're going to look at LRC circuits. The RC circuits will have resistors and capacitors. The LR circuits will have inductors and resistors. And the LRC circuits will have all three components, inductors, capacitors, and resistors. And we will look at them in two configurations, parallel circuits and series circuits. The circuits that have only one energy storage component, such as a capacitor or an inductor and a resistor, those will be first order circuits as given by the differential equation that describe them. And the ones that have all three components, the LRC circuits, will be second order circuits according to the differential equation that will describe such circuits, both the series and the parallel circuits. The other topic that we're going to be looking at is dependent sources, and we'll see how different sources can depend on other quantities in the circuits. Let's look at the two key concepts that are going to enable us to understand the transient behavior of both first order and later second order circuits with capacitors and inductors. If we go back to the differential equation that describes the current in a capacitor as C dV dt, so the capacitance times the time derivative of the voltage across the capacitor, we can infer two very important lessons from this equation. The first one is that for that derivative to be finite, as it should, the voltage across a capacitor cannot change instantaneously. The other key concept is that if the voltage is not changing, then the current through the capacitor is zero, because the derivative will be zero. What that means is that for DC circuits, when the voltage is not changing, the capacitor will look like an open. If we look at the equation that describes the voltage across an inductor as the inductance times the time derivative of the current through the inductor, we see that for that derivative to be finite, as it should, the current through an inductor cannot change instantaneously. Additionally, in DC circuits, where the current is not changing, where the current is constant, that derivative will be zero, and therefore, in DC circuits, an inductor will look like a short or a wire. So what we will be doing is analyzing both RC circuits and RL circuits separately. We will not mixing capacitors and inductors in these circuits. These are so-called first order circuits, as we'll see, and as given by the differential equation that describe them. So we're going to be utilizing the techniques that we already saw, such as nodal analysis and mesh analysis, to find the expressions for the voltages and the currents. Then what we're going to be doing is applying these concepts that I just mentioned to find out what are the initial and final values and plug that into the resulting equations to get a complete expression. If we look at the equation that we get from applying nodal analysis or mesh analysis to a first order transient circuit with resistors and capacitors, or with resistors and inductors, we will get an equation of the form like this: a first time derivative times a linear component equals to some type of forcing function. And this derivative will correspond to the current in a capacitor, and this term will be the resistive term, or in RL circuits, this derivative will correspond to the voltage across an inductor, and this term will be the resistive component. The form of the general equation that is the solution to the differential equation above is x equals to k1, a constant, plus k2, another constant, times e to the minus t divided by tau. For an RC circuit, tau is the Thevenin equivalent of the resistors in the circuit times the capacitance, and for an RL circuit, tau is the inductance divided by the Thevenin equivalent of the resistors in the circuit. These are the resistors in each case that apply to the capacitor or the inductor in the first order transient circuit. And in general, we'll see that the constants K1 and K2 respectively are the value of the current or the voltage, whatever case this x of t is, after a very long time. And we saw how the concepts that we reviewed at the beginning can help us with that. And the constant K2 is the difference between that initial condition for a voltage or a current right after we start measuring, or an infinitesimal amount of time right after t0 minus that value after a long time, times the exponential term of e minus t divided by tau. This is a pictorial example of the meaning of the time constant. If we have a circuit that has a form of k2 times e to the minus t divided by tau, meaning that after a long time the value of the function is equal to 0, as we see here, we see that the function is going to start with the value of k2. And if we go back to the general form of the equation, it supports that. Also, here we can see two values for tau. If tau is 4 seconds, then the decay is going to be much slower than if we had a smaller value of tau, such as this one, where tau is half a second. Now let's look at second order transient circuits. We have two types of second order transient circuits that we're going to be looking at. One is the parallel RLC circuit with a forcing current source, a single node voltage, and we're going to solve for the current through the inductor. The other one is a series circuit where we have a resistor, a capacitor, and an inductor with a forcing voltage source, a single current, and we're going to solve for the voltage across the capacitor. For the parallel circuits, if we write the nodal equation at that single node, we have that the current through the resistor plus the current through the inductor plus the current through the capacitor is going to be equal to the source current. And if we manipulate that equation, we get a second order differential equation that looks like so. For the series circuit, we can write a loop equation, and we get that the voltage across the resistor plus the voltage across the capacitor plus the initial voltage across the capacitor plus the voltage across the inductor is equal to the source voltage. And if we manipulate that equation, we get this second order linear ordinary differential equation. If we manipulate further the previous equations, making sure that the second order derivative has a coefficient of 1, we can put those equations in this form of the auxiliary equation for those second order differential equations, where S2 plus 2 theta omega naught times S plus omega naught squared is equal to 0. The general solution to that auxiliary equation is the following. That auxiliary equation in general is going to have two roots given by minus theta times omega naught plus omega naught times the square root of theta squared minus 1 and minus theta omega naught minus omega naught times the square root of theta squared minus 1. And the general solution of that equation is going to be a constant k1 times the exponential term of e times the first root times t plus a second constant k2 times the exponential term of the second root s2 times t. And to find out the values of k1 and k2, we have to use the initial conditions, going back to the concepts of the behavior of current and voltage in a capacitor and an inductor, and formulate that the initial value is going to be equal to k1 plus k2, and that the first derivative of the solution equation evaluated at t equal to 0 is going to be equal to s1 times k1 plus s2 times k2. So we have two equations and two unknowns, and that will allow us to find the actual values of k1 and k2. For the roots, we have three different cases. The first one is theta is equal to 1. We can see that the term under the radical is going to be greater than 1, and this part of the expression is going to be real. Therefore, the whole expression is going to be real. In that case, when theta is greater than 1, S1 and S2 are going to be two distinct real roots. And the general equation for the solution is going to be k1 times e to the minus s2 times t plus k2 times e to the minus s1 times t. The next case is when theta is less than 1. In that case, the number under the radical is going to be less than 1, and this expression is going to be imaginary. Therefore, in that case, S1 and S2 are going to be two distinct complex roots that are complex conjugate of each other because of the different signs in these expressions. In that case, another way of writing the roots is minus sigma plus j omega d and minus sigma minus j omega d. The general form of the equation is going to be e to the minus theta omega naught t times a1 times a cosine term with a coefficient of omega naught times the square root of 1 minus theta squared times t plus a2 times a sine term with a coefficient of omega naught times the square root of 1 minus theta squared times t. And the third case is when theta is equal to 1. In that case, this term is going to be 0, and we're going to have two repeated roots that are real, and they are equal to minus theta times omega naught. In that case, the general form of the equation is a constant times e to the minus theta omega naught t plus another constant times t times e to the minus theta omega naught times t. Pictorially, the response of these three cases look as follows. This is the critically damped case, this is the overdamped case, and this is the oscillatory underdamped case. So if we look at the three cases, and if we look at the form of the equations that we get by applying either nodal analysis or loop analysis, and we take the forms of the coefficients in the equations, we can find the values of theta and omega naught in terms of the resistor, the inductance, and the capacitor. Furthermore, if we apply the concepts of the initial conditions as given by the very general solution of those second order differential equations, then we can use the special cases for the underdamped, the overdamped, and the critically damped cases and find the values of the constants in the solution equations. Now the next topic in this submodule is the dependent sources for DC circuits. And we have four variations of them. First, we can have a voltage dependent voltage source, which its voltage will depend on some constant times another voltage in the circuit. Or we can have a current dependent voltage source whose voltage is going to be dependent on a constant times a current in the circuit. And we can also have a voltage dependent current source, and the current is going to be dependent on a voltage in the circuit. And finally, we can have a current dependent current source whose current is going to be dependent on a constant times another current in the circuit. All the techniques that we have used before for analyzing DC circuits will apply to DC circuits with dependent sources, except that additionally we're going to have these equations that describe the dependency of the sources as an additional equation in our system of equations to solve the circuit and analyze it for any type of current or voltages in the circuit. And this concludes submodule 3.1, the first one in module 3, which treats other topics in the course.